Gaze up at the night sky, a canvas painted with the silent, eternal dance of stars. For millennia, humanity has looked upon this cosmic tapestry, assuming that every flicker, every celestial ballet, is a product of natural forces of physics and chemistry playing out on a grand scale. We have learned to decipher the language of supernovae, the gravitational whispers of black holes, the rhythmic pulses of distant pulsars. Our understanding of the universe has grown exponentially, revealing a cosmos of breathtaking beauty and predictable, albeit complex, phenomena. But what if, amidst this grand, natural order, there appeared a signal, a pattern, so utterly bizarre, so profoundly unnatural that it forced us to question everything we thought we knew? What if a distant star began to behave in a way that defied all known astrophysical explanations, hinting at something far more extraordinary, something that whispered of intelligence on a scale almost beyond comprehension? This is not a hypothetical thought experiment. This is the true story of Tabby's star, a cosmic anomaly that sent ripples of excitement and disbelief through the scientific community and captured the imagination of the world. Its discovery was not made by seasoned astronomers poring over complex data, but by a group of citizen scientists, volunteers participating in the Planet Hunters project. Their task was to sift through the vast trove of light-curve data collected by NASA's Kepler Space Telescope, a mission designed to detect exoplanets by observing tiny dips in a star's brightness as a planet passes in front of it. These dips are usually regular, predictable, and shallow, like a tiny moth fluttering across a distant streetlight. But what they found with KIC 8,462,852, now famously known as Tabby's star after its lead researcher Tabitha Boyajian, was anything but regular or shallow. The star, a seemingly ordinary F-type main sequence star located about 1,470 light-years away in the constellation Cygnus, exhibited erratic, unprecedented dimming events. Its light would drop not by a mere fraction of a percent, as expected, from a typical exoplanet transit, but by as much as 22%, sometimes for days or even weeks, before returning to normal. These dips were not periodic. They were irregular, asymmetrical, and varied wildly in duration and depth. It was as if colossal, oddly shaped objects were passing in front of the star, blocking its light in a chaotic, unpredictable dance. No natural phenomenon could adequately explain such a bizarre and dramatic light curve. The initial data from Kepler showed a series of these inexplicable dimming events over a 4-year period, with some dips being much more pronounced than others. One particular event, dubbed the Anomaly dip, saw the star's brightness plummet by 15% over a few days, while another, the Celia dip, showed a staggering 22% reduction in light. These were not minor fluctuations, they were massive, prolonged obscurations of a star's light, unlike anything astronomers had ever witnessed. The scientific community was baffled. Was it a massive dust cloud? A swarm of comets? A planetary collision? Each natural explanation seemed to fall short, unable to account for the sheer magnitude, irregularity, and duration of the dimming. The star was, quite simply, behaving in a way that defied all conventional astrophysical wisdom, screaming out its status as a true cosmic anomaly, with natural explanations struggling to fit the data. The scientific discussion took a turn into the realm of the truly speculative, yet undeniably captivating. If no natural phenomena couldn't explain the star's bizarre behavior, what else could? This is where the alien megastructure hypothesis entered the scene, igniting a firestorm of debate and public fascination. The idea, first proposed by astronomer Jason Wright and his colleagues, suggested that the irregular dimming could be caused by an artificial structure, a colossal feat of engineering built by an advanced extraterrestrial civilization. The most compelling concept put forward was that of a Dyson swarm or a partial Dyson sphere. A Dyson sphere, first theorized by physicist Freeman Dyson in 1960, is a hypothetical megastructure that completely encloses a star to capture a significant portion of its energy output. While a complete sphere is likely impractical, a Dyson swarm, consisting of numerous independent structures orbiting a star, could achieve a similar goal. These structures, perhaps vast solar collectors, habitats, or manufacturing facilities, would block varying amounts of the star's light as they moved, creating the irregular, non-periodic dimming patterns observed from Tabby's star. The sheer scale of the dimming, up to 22%, suggested objects far larger than any known planet, objects that could only be artificial in origin if they were to account for such a significant blockage of starlight. The appeal of the alien megastructure hypothesis was undeniable. It offered a tantalizing glimpse into the possibility of intelligent life beyond Earth, not just in the form of microbial traces or faint radio signals, but as a colossal, tangible presence in the cosmos. It spoke to humanity's deepest curiosities about our place in the universe and the potential for civilizations far more advanced than our own. The idea resonated with the public, sparking widespread media coverage and discussions across the globe. While many scientists remained cautious, emphasizing the need for more data and natural explanations, the sheer audacity and intriguing nature of the alien megastructure concept ensured that Tabby's star became a household name, a symbol of the tantalizing possibilities that lie hidden in the vastness of space. It was a moment where science fiction seemed to brush against scientific reality, pushing the boundaries of what we dared to consider. Following the initial excitement and the sensational alien megastructure hypothesis, the scientific community embarked on a rigorous and methodical investigation to unravel the mystery of Tabby's star. This was a classic example of the scientific method in action: observe an anomaly, propose hypotheses both natural and artificial, and then gather more data to test those hypotheses. Astronomers turned every available instrument towards the enigmatic star, from ground-based telescopes to space-based observatories like the Spitze Space Telescope and the Hubble Space Telescope, hoping to catch another dimming event in real time and gather more clues. One of the leading natural explanations that emerged was the cometary swarm hypothesis. This theory suggested that a large family of comets, perhaps disrupted by a passing star or planet, had fragmented and were now orbiting Tabby's star. As these comets passed in front of the star, they would release vast amounts of dust and gas, causing the observed dimming. The irregular nature of cometary orbits and the unpredictable release of material could potentially explain the erratic dips in brightness. However, this hypothesis faced challenges. For such a large amount of dust to cause a 22% dimming, the comets would have to be truly enormous, and the dust would need to be relatively opaque. Furthermore, the dust should emit infrared radiation as it absorbs starlight and heats up, but initial observations did not show a significant excess of infrared light, making the cometary dust explanation less straightforward. Other natural explanations were also considered and largely ruled out. Stellar pulsations, where the star itself expands and contracts, causing changes in brightness, were inconsistent with the observed dimming patterns. Instrumental errors with the Kepler telescope were thoroughly investigated and dismissed. A large, fragmented planet or a swarm of asteroids colliding could produce dust, but the sheer amount and duration of the dimming made these scenarios less probable. The challenge was that no single natural phenomenon seemed to perfectly fit all the observed characteristics of the dimming events, leaving a lingering sense of unease and a continued openness to alternative explanations, even the most extraordinary ones. The ongoing monitoring of Tabby's star eventually provided crucial new data. In 2017, the star began dimming again, and this time, astronomers were ready.